Okay, dear colleagues, dear guests, dear ladies and gentlemen, it is our great pleasure to welcome you with Barbara at this opening plenary session of the ICHEP 2024 conference. And we will now invite Zdenek Dolezal, the chair of the organizing committee of the ICHEP conference, to welcome you at the plenary sessions.
Ladies and gentlemen, dear colleagues, dear guests, it is my great privilege to welcome you at the 42nd International Conference on High Energy Physics. The conference, dubbed also the Big Rochester, has become throughout its 70-year history undoubtedly the leading conference in our field. The first Rochester, organized by Robert Marshak at the University of Rochester, USA in 1950, was a one-day meeting hosting 25 participants. It took years till this conference became larger and international. The meetings contributed hugely to the exchange of information in the pre-electronic era. Just one example, it was here where the regular summaries of particle properties became collected and gave birth to the famous PDG booklets. Recent decades saw ICHEP growing in all parameters. The geographical pattern from the 60s, USA, Western Europe, Soviet Union, was extended to cover all regions, and the organization of the conference was overseen by IUPEP C11 Commission on Particles and Fields. It was 8 years ago when the ICHEP organization was assigned to Prague. It was the 2020 edition. But the pandemic came and the ICHEP 2020 moved to the online format. It obviously lacked most of the ingredients of a scientific conference, but it attracted over 3,000 participants, almost triple of the typical number. Nicely, we have been given a second chance. ICHEP 2024 is in Prague, and it is quite a standard one. Its 1,350 registrants listened last week to 900 parallel talks, saw 300 posters, and gathered here now to enjoy 40 plenary talks and 2 important panels. One will take place today over lunch and will deal with the important topic of outreach and education. The second one will bring together directors of the key particle physics laboratories to discuss the strategy of our field in the world where COVID is gone, but many other challenges and crises remain or arise. To organize such a conference, the whole particle physics community in the Czech Republic, coming from 5 universities and 2 research institutes, joined forces, supported by the ministries, institutional managements, international labs, as well as private sponsors. All these sponsors are listed on the web. Let me get back to comparing 2020 and 2024. The past one was surely an important conference, but reminded us the quote of George Walt: "It would be a poor thing to be an atom in a universe without physicists." It was indeed a weird thing to have an ICHEP without physicists. Let me thank you very much for getting the ICHEP back on track and wish you an enjoyable and fruitful conference.
Zdenek, thank you very much for the warm welcoming words. And now it's our pleasure to invite Professor Radka Vildová, Director General for Higher Education, Education, Science and Research Section at the Ministry of Education, of Youth and Sports of the Czech Republic.
Dear guests, dear colleagues, it's my great pleasure to welcome you in Prague and to give a few introductory words on the opening of International Conference on High Energy Physics in 2024. I am very happy to finally see you here in the year of 70th anniversary of CERN, as the last time the conference was moved to online due to COVID. The Czech Republic and Czech scientists participate in almost all major particle physics projects in the world, and the Ministry of Education, Youth and Sport is proud of that. I am sure you know that the Ministry of Education, Youth and Sport is the central public administration body which is responsible for science, research and technology, development, policy making, and public funding, including international cooperation of Czechia in research and innovation. From this position, the ministry supports Czech participation, 17 large research infrastructure in physical sciences and engineering, with operation cost around 13 million euro per year and total investment 37 million in the years 2023-2026. Besides of that, the ministry supports Czech membership in ERIC with contribution around 38 million euro per year and European Spallation Source ERIC. And I, of course, cannot forget on membership in CERN with a contribution of about 40 million euro per year, ESO 2.6 million euro and ESA 14 million euro. Of the 17 large research infrastructures in physical sciences and engineering, I can mention BNL-CZ, CTA-CZ, FAIR-CZ, Fermilab-CZ, OSER-CZ, which are well related to high energy physics. Of course, there are CERN-CZ as well, devoted to support experiments at CERN. And what is not less important, the ministry supports also higher education, including international peer review assessment and institutional and project funding of 26 public and 2 state higher education institutions. Dear guests, dear colleagues, ladies and gentlemen, on behalf of me and my Minister of Education, he is today at the other business trip out of Prague, I wish you a very successful conference and do hope that you will enjoy not only Prague, but also this conference. Good luck and thank you for the invitation.
Thank you very much, and we are very happy to have with us also the rector of the Czech Technical University in Prague, Wojciech Petráček, whom I would like to invite now to say us a few words.
Good morning, dear colleagues, ladies and gentlemen. I'm really very happy that we are meeting here on this fantastic ICHEP 2024 conference in Prague. And I'm very happy not only as a rector of the Czech Technical University, but also a physicist, because I'm originally from ELIS and from GSI experiments also. So for me, that would be so nice to be here with you all the time. That would be nice, and to listen to all the talks which will be held here. But unfortunately, as a rector, I cannot spend here more time. But definitely, that's a result of many years of preparation to be here today and in past and future 3 days. And I hope you will enjoy the plenary talks and all the nice things which will happen still during the conference. I hope you will also enjoy the conference dinner tomorrow in Bethlehem Chapel, which belongs to Czech Technical University, and there I will have the privilege to be also for some time with you. So I would like to thank to all of you that you came to Prague and to be here for sharing of the most recent physics results in high energy physics. I would like to thank to all of organizers, and among them also to our team from Czech Technical University and the Institute of Physics and other institutes of academy here in Prague and Charles University. And it's a great days for us really to discuss this top-end physics here in Prague. So enjoy the conference and enjoy the stay in Prague, and have a nice stay here. Thanks for your attention.
Thank you very much, and it's our pleasure to have with us today also Vice President of the Czech Academy of Sciences, Jan Řídky.
Good morning, ladies and gentlemen. Welcome in Prague. I would like to greet you on behalf of the Czech Academy of Sciences. In Czechia, the Academy is not a learned society. It's a group of 54 institutes which cover basically all branches of science. And altogether, they have about 11,000 employees. The most notable institutes and those which are concerned by high energy physics is Institute of Physics and Institute of Nuclear Physics. Institute of Physics is the biggest institute of the Academy. So for us, the program of high energy physics is an important one, and we follow its progress, and of course we are concerned with the plans for the future. To my mind, physics could be in two states. One state is that there are more unexplained phenomena and theories try to explain them, and the other is that there are many theories which we cannot resolve by the measured data, and in this state it's clear that the emphasis has to be put on further experimental endeavor. So I know that high energy physics stands now before big decisions which will influence its future for many decades. So I hope that also this conference will contribute, that we will find ourselves in more clearer position concerning the data and the direction where to go in the future. So I hope that this conference will contribute to this, that you will enjoy your stay in Prague, and you will enjoy the conference. So please take my greetings on behalf of the Academy. Thank you.
Thank you very much. And we have one more distinguished guest with us. It is the State Secretary of the Ministry of Foreign Affairs of the Czech Republic, Magister Radek Rubeš.
Thank you. Dear Director General, Ms. Giannotti, dear Director General of the Ministry of Education, Ms. Vildová, distinguished guests, ladies and gentlemen, it's my great honor to attend the opening ceremony of the 42nd International Conference on High Energy Physics, and to welcome you in Prague as the representative of the Ministry of Foreign Affairs of the Czech Republic. This world-class event has attracted top representatives of the field, physicists, researchers, academics, as well as representatives of international institutions, including the world-famous European Organization for Nuclear Research. I'm glad that this year's edition is being held here in Prague, because Czechia has a rich history in the field of natural sciences and physics. As a representative of the Ministry of Foreign Affairs, I must emphasize that in order to maintain a level of excellence in these fields, it is essential to develop international cooperation, to share the results of studies and to coordinate research. This will ultimately lead to not only more significant discoveries and patents, but at the same time will contribute to the trustworthiness of the research itself and to the security of like-minded countries. Notably, the field of particle physics, with its well-developed international cooperation, can serve as a good example of the international cooperation. Events like today's represent a great opportunity to further develop science, not only in Czechia, but also worldwide, and to strengthen international connections. In this spirit, it is important to mention that in its program declaration, our government committed itself to support modernization and increase the competitiveness of Czechia. The Ministry of Foreign Affairs, together with institutions responsible for research, development, and innovation progress, contribute to this goal in particular by supporting Czech research, development, and innovation abroad. Last year, we have therefore added the agenda of science diplomacy to the portfolio of our diplomatic network and will continue to further support the connection of Czech science with the world. This, additionally to the 3 specialized Czech science diplomats abroad, there is a network of 116 embassies, general consulates, and others and contact offices ready to promote the attractiveness of the Czech higher education system, the extensiveness of our research institutes, as well as the capacities of large research infrastructures with international participation. Czech science diplomacy also opens doors to the new opportunities of cooperation, with an emphasis on export support, transfer of knowledge and technology into practice, as well as for commercialization of research results and innovative solutions. What is equally important, and what I see as my duty as State Secretary to mention, is the role of Czech scientific expats abroad. Whether working in academia, research, international institutions, or multinational companies. It is thanks to these amazing people that science diplomacy takes on a new, deeper dimension and can serve to establish intensive contacts and to better promote Czech science abroad. I will mention one example, namely Czech participation in CERN research. The number of Czech CERN users, that means scientists involved in CERN research, is 230, of which approximately 1/3 are students, which represent more than 2% of all CERN users. Czech researchers are involved in a number of experiments and projects at CERN, the most important of which are Atlas and Alice, which is the, I don't understand even, the heavy ion collision detector, etc., etc. Czechia does not participate in CERN research, does not only participate in Czech research, it also contributes significantly to development of CERN capacities. Scientists from Czechia participate in defining CERN research and developing detector technology. Czech companies supply CERN with high-tech products and common goods, also cars and others. The quality of the Czechia's cooperation with CERN is evidenced by the fact that our country's membership in CERN was evaluated in 2021 by an international evaluation panel of leading European experts as a model example of the use of membership in an international infrastructure organization and a shining example of international cooperation in large-scale research. Last but not least, this year CERN commemorates its 70th anniversary. 70 years of research, of which Czechia, as former Czech and Slovak Federative Republic, has been a part for more than 32 years. And I would like to wish this exceptional organization many, not only scientific successes, and reaffirm our commitment to continue collaborating with CERN on such an outstanding basis. I wish you all a very fruitful conference, and please enjoy the beauty of Prague. Thank you.
Thank you very much. And before we go to the physics program, let me invite the second chair of the ICHEP organizing committee, Tomas Davidek, to tell us some practical information for the rest of the conference.
So, good morning. Good morning, ladies and gentlemen. I would like to join my previous speakers in welcoming you to Prague and to the ICHEP plenary sessions. So I have just few practical information for you. So there will be the education and outreach discussion session during the lunchtime today in Terrace 2A. So those who are interested are welcome. Then we will have a conference photo tomorrow, just before the coffee break in the morning. And then there are two social events, ICHEP party tonight and conference dinner tomorrow evening. But these are for people who have tickets, because the places where we don't have enough places for everyone, so just those who were succeeded in buying tickets, you are welcome to join. And all details are available in the Indigo page, as well as in the two conference applications, Conference for Me and HEPCON. And then I would like to draw your attention to the exhibition on the ground floor, where we have, let's say, 4 exhibitions. The main one, I Want to Be Human, which is an international touring exhibition. And then Be Inspired at ICHEP 2024, which is the exhibition of science meeting arts. And then World of Particles, some cartoons, and also some history of this conference center in a nutshell. So thank you for your attention and enjoy the conference.
Thank you, Tomas. Thank you all the guests with us to us. So let's thank everyone again. Now we will be moving to our scientific part of the conference. So we'll start with highlights from different experiments. It will be divided into 2 parts now before the coffee break, and then later after the coffee break. So we're going to start with Atlas highlights by Monica Dunford, please.
Many thanks for being here, and also many thanks to the organizers for this incredibly organized conference. It's fantastic. I'm going to be giving you a few highlights from the Atlas detector experiment today. And while we have many new results that have premiered at ICHEP for you, I'm going to focus on only a small subset of those results. And I'm going to talk about the areas of fundamental parameters. I'm going to talk about dynamics and symmetries, and finally I'm going to close on electroweak symmetry breaking. Now, and I've chosen this handful of results because I think they exemplify the progress that we've made during Run 1 and Run 2 of the LHC. And also, they're going to demonstrate the progress that we can make as we go into Run 3, which is the data-taking phase we're in now, and then ultimately the High-Lumi LHC. And throughout this talk, I'm going to try to focus on points of improvement, points of innovation that we can do in the future, near future, and far future, so that we can continue to push the barriers in fundamental interactions. So we have a very deep understanding of fundamental interactions, and it's like it's a tightly woven tapestry. So, and that tightly woven tapestry is very important, because what I mean by that is that if you wish to play in one area of the standard model, it will have large-reaching consequences in many, many other areas. And that tightly woven tapestry, that interconnection, that over-constraint, is one of the standard model's greatest tools. It's one of its greatest powers. An excellent example of that is shown here in this figure, which is a measurement of the W mass, a measurement of the top mass, and then the determination of those masses via precision electroweak parameters. And as we improve the precision of our results, we tighten that tapestry and thereby reveal inconsistencies and gaps in our knowledge of fundamental dynamics. So where do we stand after 2 runs of the LHC? Well, we've measured the masses very precisely. We start to, for example, reach the sub 0.1% level on the Higgs mass. We've measured many fundamental parameters. I show in one example here, which is the example of the strong force, where we're now less than 1%. The strong force coupling is one of our least known fundamental parameters, and it touches many, many areas of the standard model. So therefore, knowing it precisely is important in order to tighten that tapestry. And finally, we've been able to do a lot of fun things with our data. So for example, this is one example where we have observed entanglement between 2 top quarks. And it's the first observation of entanglement at such high energies, and also amongst quarks. So one result I want to highlight for you today is a recent measurement of the W width. Measurements of the width are very powerful because they tell you what a particle is coupling to. And therefore, by comparing the measured width to its expectation, you can determine if there's unknown couplings. This is a recent result that we have, which you can compare to a variety of other measurements from other experiments. And this measurement is dominated by systematic uncertainties, where the systematic uncertainties are coming from those of the calibration, for example, the electrons and muons, coming from uncertainties on the theoretical modeling, and then also uncertainties on the parton density functions. And this trilogy of systematics is going to feature itself. It's going to be a theme that reoccurs through many of our precision measurements. And one of our major targets for the current data taking and also the future is to really improve upon these areas. I'm going to show you an example of how that can be done in this measurement here. This is a measurement of the WPT distribution, where we took this measurement under very ideal data-taking conditions of the LHC. So basically, it was running in low pileup, and I'm running at 2 center of mass energies, where our detector is most optimal. And as a result of that, by using those special data-taking conditions, we're able to measure the WPT distribution. So this is at 5 and 13 TeV. We're able to measure that WPT distribution very precisely. And we're going to use that data to help improve the theoretical modeling, and that's going to feed directly back into, ultimately, improvements in, for example, precision of the W mass. Now, a second result I want to highlight is a measurement, a test of lepton universality. This is where we look at TT bar events where one W decays to electrons and the other decays to muons. And through a very carefully defined measurement, almost painfully defined measurement, we're able to cancel all of the systematic uncertainties and obtain a very precise result, which is even more precise than the world average. Now, this result, this methodology is very powerful. It's also been used, we also used it a few years back in order to measure the universality of taus versus muons, and that solved a sort of age-old puzzle from LEP, where we had seen a discrepancy there. Finally, a third result I want to highlight is a measurement of the coupling between the Z boson and the top. Now, this coupling is very poorly understood, or poorly constrained, and so therefore it's very sensitive to potential new physics contributions. And again, through a real tour de force in the analysis methodology, really expanding the analysis phase space, really improving many of the systematic uncertainties, we're able to make a big improvement in the precision, a factor of 2, to obtain some very precise results. And then we use this distribution, for example, what's shown here is the PT of the top. We use this distribution to therefore search for anomalous couplings of the top to the Z and thereby constrain them. So where can we go in the future? How can we continue to improve our precision results and help and tighten this tapestry in order to reveal inconsistencies and gaps? Well, one of those is as I said, our dominant systematics are, one of them is the measurement, the systematics related to the calibration. And over the past couple of years, we've really made quite a few innovative improvements to improve these greatly. I'm going to show 2 examples. In this figure above me, I don't want to go into the details, but this is the energy of the electron. And I don't want to go into the details of the plot, but I just draw your attention to the light versus dark blue. And that's how we've been able to, using the data itself, to constrain this uncertainty. And it was because of this improvement that we've obtained this very precise Higgs mass. The second example I want to show is new, which is using tau decays, where the tau comes from either a single W or from a W from TT bar. And you look at the tau decaying to a single pion, and you can use that as a very precise, almost like in situ test beam. And you compare the energy that the tau deposits in the calorimeter versus its momentum, this E over P, and you can use that to constrain the jet energy scale. And what you see by comparing the dash versus the dark line is the improvement we're able to obtain, especially at very high PTs in the jets, to obtain an extremely precise energy scale of the jets. Now, I think in Atlas and well as CMS, we've really made incredibly innovative improvements in terms of the jet energy scale, and both experiments are operating much beyond their design energy, their design goal for jets. So we have a very deep understanding of interactions, and we've used that to make many beautiful measurements, and we've also used that to compare them to stunningly accurate theory. So the question about, as we search for what is beyond the standard model, although the parameter space of beyond the standard model is vast, it is not unguided. And one of the guiding principles of the standard model where it was built was the idea of imposing symmetries upon the Lagrangian. And that concept and that idea continues to guide us as we search for physics beyond the standard model. So in this diagram, this is merely a graphical representation of the different areas that we look for when we search for beyond the standard model, the symmetries and dynamics that we're after, and also the reasons why we do it. Now, after 2 runs of the LHC, we've done a very extensive search for new dynamics and symmetries, and take this with a grain of salt, because there are many, many pockets of areas where we're not able to look yet, but we have excluded most of these areas around a 1 TeV to the multi-TeV region. Now I'm going to highlight 2 searches in this talk, both of which use new data from run 3. So the first is a search for supersymmetry, which has an innovation that in the sense of the triggering system, we're able to now reconstruct events that have a large impact parameter. So what do I mean by that? When couplings, as a general rule, if you have a particle that has a very small coupling, it can be long-lived. And in this example here of these SUSY particles, they can be long-lived, and then therefore our tracking is not designed to look for events that have large radius, that have large impact parameters. One of the major innovations of the LHC during run 2 was to innovate the tracking so that we could search for these large impact parameters. It's called so-called large radius tracking. The innovation here has been now to incorporate that so that it can be done online fast enough inside the trigger. And as a result of that, together using some precision timing information from the calorimeter, which you can see up top here, we're able to, even though we have a small subset of data compared to run 2, we're able to greatly increase the exclusion here shown for the mass of a tau, supersymmetric tau particle, greatly beyond, just beyond what we did for run 2. So higher masses as well as longer lifetimes we're able to target now. The second example I want to show is a search for magnetic monopoles. This was data that was taken at the end of last year, so very new data for us. Again, new triggers was the real innovation here, where we were able to select a data set that can now look for magnetic monopoles. This was done in ultraperipheral lead collisions, so lead collisions have very high electromagnetic fields, which make them an ideal case for producing monopoles. And this data set of using ultraperipheral collisions, where basically the 2 lead collisions pass by each other, to create a high flux of photons and basically turns the LHC into a photon collider. We've used that data set for many innovative things. For example, light-by-light scattering was observed in that data set. Measurements of tau G-2 have been done with this data set. And now we're going to use it to produce and search for monopoles. You can see we can't reconstruct these tracks like normal tracks because magnetic monopoles don't bend in the magnetic field like electrically charged particles do. So as a result, we use a variable that's called like a transverse thrust to reconstruct the direction. And as a result, because we have now been able to select a much larger data set of these kinds of events with our new trigger, we're able to set limits that are about close to a factor of 10 better than previous experiments. So finally, I want to close on the topic of electroweak symmetry breaking. The question of who breaks electroweak symmetry is one of the most important topics that the LHC can answer. And it's a question that involves a lot of ingredients. It's a question that has to be squeezed from many sides. And those ingredients are, we need to know precision Higgs, we need to know the couplings of the Higgs very well. We want to understand vector boson polarization. Longitudinal polarization is a consequence of electroweak symmetry breaking. And so therefore, this scattering of two longitudinally polarized bosons is very sensitive to who is exactly at play in the middle there. Finally, we want to understand the Higgs coupling, the Higgs potential, and we do that via measurements of the Higgs coupling. And we can also look for extended Higgs sectors. Now, one of the very hot topics, or one of the very hot questions today, is whether or not the universe underwent a strong first-order phase transition as electroweak symmetry was broken. In other words, did the universe boil when we transitioned into the broken electroweak phase? Now, one thing we know about our Higgs, this Higgs, the 125 GeV Higgs, is that, well, it doesn't boil the universe. So if the universe boiled, then we know that we have another player in the game of electroweak symmetry breaking. And we can search for that, test for that at the LHC via tests of extended Higgs sector. So where do we stand after 2 runs of the LHC? Well, we have very precise measurements of the Higgs couplings. So for example, we're starting to approach the 5% level, and we're starting to target second generations within Higgs. We have observation and evidence of longitudinal polarization in WZ and ZZ. This is a really tremendous achievement involving very innovative machine learning methodologies, plus incredible innovation on the theoretical side to make this possible. We're starting to approach the standard model prediction for di-Higgs cross-sections, again through tremendous innovation on the analysis methodology. And we've done extensive searches for extended Higgs sectors. I will only briefly highlight a very new example that we have here, which is a combination of search for charged or multi-charged Higgs. And you can see we've combined 2 results in order to improve our limits. I will touch upon this briefly because this is going to be discussed in much more detail in Nicola's talk later today. But this is an example of our recent combination of di-Higgs production. And you can see that we've added several new channels as well as improved the others to now start to be about 2.5 times away from the standard model. Instead, I want to focus on a couple of recent results in terms of precision Higgs. This is a measurement of TTH going to BB. Now, measurements of TTH are very important because they're our only direct way of measuring the coupling of the Higgs to the top quark. Through a variety of analysis improvements, expanding the phase space, better analysis methodologies, as well as improvements to the uncertainties on the theoretical modeling, we're able to greatly improve the precision here by a factor of 2, and we start to approach observation of about 4.6 sigma. Again, I come back to this trilogy of systematics that I was talking about, and the modeling being one of them. This example of the TTH result is another example of that. And one of the ways that we can improve upon that is to, again, make dedicated measurements in order to help improve the modeling. This is yet another example of that, where we've now measured TT bar plus heavy flavor, which is one of the dominant uncertainties to the TTH measurement. And you can see we compare them up to a whole variety of theoretical predictions, and we use these results in order to improve the modeling and therefore improve our result of TTH. We have a lot of other results of that nature, and I think as we continue to do this, it's very important if we want to make continued progress in some of these precision results. The second Higgs result I want to highlight today is a measurement of VH to BBCC. Again, we have improved the modeling, improved the methodology, and have therefore improved both our measurement of VH-BB as well as VHCC. We've been able to improve our limit, because we haven't observed VH to CC yet, by a factor of 3 as a result of this, and we now start to approach about 10 times the standard model in measuring this second generation coupling to the Higgs. Again, I'm not going to touch upon this briefly because I think it's going to be mentioned several times later, but one of the major innovations that we've had over the last couple of years has been the use of machine learning inside of, in particular, identification, B tagging or C tagging. And you can see that this result, this is year of development of our various taggers and looking at their rejection, the improvement in their acceptance versus their rejection. You can see that this result, even though we have a factor of 3 improvement, you can see that in the pipeline we have many better improvements coming, and I think we'll continue to see that trend. So I'm going to briefly close on just where we can go ultimately for the future, because we have most of our luminosity is yet to come at the high Lumi LHC. And the high Lumi LHC is by every definition a Higgs factory. I mean, to put it simply, what would you do with 400 million Higgs bosons? And our detector, of course, has to step up accordingly to be able to handle the large luminosity and the high data taking rates. So one of the things that we're building right now, you can see that I have sort of a microscopic and macroscopic view. This is the arrival of our outer barrel, which has just arrived into its clean room location and is starting production. And this is the small picture, is an example of some of the pixel detectors that will go in it. Now, one thing I want to highlight about this tracker is that not only is it meant to cover much harsher conditions, it also has improved granularity, improved coverage, and that's what you can see in this figure here. So this is the resolution on the impact parameter. Lower is better. And you see that with the new tracker, which is in red, we have a better resolution and more coverage. Just to cite a few examples of where the physics will benefit from this extended coverage. For example, sine squared theta W, which relies heavily, or any forward-backward asymmetry, relies heavily on forward electrons. Measurements of polarization rely heavily on forward jet production, and also anything with B-tagging will benefit from the extension of the coverage. Finally, our trigger system also has to keep up to pace. I showed you 2 examples of 2 searches that were not possible before we have innovated our trigger system, and our new trigger system will also have to continue to keep pace. It will be faster, more digital, and higher data rate capacity. So in short, the future is bright, but so is today. We are in the middle of a data-taking phase, and we have lots of 1.5 years or 1+ years to go with data taking. I was only able to highlight a few of the results that have premiered at ICHEP here, but I refer you to the many excellent talks to come for more details. Thank you so much.
Thank you, Monica, for this really clear and nice overview of ATLAS results. Now we are open for questions. Thank you. Now I can see a bit more of you. Please, you will get the mic.
You pointed out that for the most part, you haven't seen Susie in the one of several TV. Could you say something about those regions that are still lurking, that are sort of the hidden, the tough corners that you haven't covered yet?
Thanks, that's a great question. So I think in general, not just related to Susie, but also related to many of these models, where it's difficult for us to search are things that we can't trigger on. So for example, if the final state particles are very soft, so if you have very small mass splittings, we have then very soft particles, and we can't really trigger on them. And the other difficulty that we have is when it looks exactly like QCD, then it's of course very difficult to separate this background from the signal. And so these are the pockets that I think in general of where we tend to look now more and more today, where we would have missed with, if it's very high PT involving leptons, we've largely excluded it because that's where our detector does best. But these sort of pockets, as I say, where the energy is low, or you're talking about long-lived particles where the efficiency of standard reconstruction is poor, these are sort of the directions that we're tending to move in today because they're the least explored, because they're most experimentally challenging.
Thank you. If you have a question, I don't see everyone. It's quite hard, so please just stand up. That's okay. Thank you. Thank you, Monica. So the talk was very clear then.
Thanks.
And it is our pleasure to welcome the speaker on behalf of the CMS collaboration, Maurizio Pierini. Maurizio, please.
Good morning, everyone. It's a pleasure to be here. I'll give you a description of the latest highlights by the CMS experiment. So CMS is many experiments at once. We certainly are probing the energy frontier with our search program at the TV, but we're also operating at the intensity frontier with our Higgs program, electroweak precision program, and others. We are certainly a flavor experiment. We have a dedicated top pro physics program and also dedicated data streams to collect samples of B quarks, C quarks, and taus. We are operating during the LHC heavier ion runs, and we are contributing both with lead and proton lead to the understanding of the physics of the quark-gluon plasma. And as a matter of fact, we're also a photon collider experiment because we're capable of isolating in the LHC data samples of photon collisions using various techniques. We're also being very active as a technology driver, innovating from the technological point of view with solutions that are then for the benefit of the entire field, thinking about the reconstruction of GPUs, real-time analysis, and applications of artificial intelligence. So now I'm gonna go guide you a little bit through all of these aspects, presenting you the latest news. So we are at the middle of our journey. We are about to complete the first phase of the LHC. Next year, run 3 will stop, and we are going to have at least 300 inverse femtobarn on disk, adding run 2 and run 3, which was the goal. And after that, we go into shutdown mode, we upgrade the detector, and by 2029, we recover data taking in a new configuration, effectively in a new experiment, that aims at collecting 10 times more data, 3,000 inverse femtobarn, by 2041. While we wait for this change, we are already operating in a very challenging mode. We're pushing our detector beyond its limits. Today, we take data with 63 simultaneous collisions, which is 2.5 times the CMS design, and it's basically just a factor 2 below what the upgraded detector will do. We're taking data at 7 kilohertz, which is 7 times what we used to do run 2, and it's 70% of what we are going to do after the upgrade. So in some sense, while we wait for the future is already now. Run 3 is going well. We collected 63 femtobarn of 22 and 23 data at 13.6 TeV. This data is what we're now currently exploiting for analysis, and it sums to the 137 femtobarn that we have from run 2. On top of that, we already collected 46 femtobarn this year. The target is to exceed the 100 femtobarn this year. So we are really increasing substantially our data set while we operate the detector with an efficiency of about 90%. We are confirming, let's say, the data collection efficiency of 93%. So 93% of the LHC delivered collisions are taken, which means the detector is up at efficiency at 90% of the time. And of this data, 97% of this data are declared good for physics. This number used to be smaller in the past. There's been a tremendous work done in order to bring this up, and mainly thanks to the deployment of artificial intelligence-based data quality monitor assessment, which makes the process much, much easier. This is a project that we've been pioneering since 2017. So we've been operating under stable performance from a physics point of view. We have a high-quality prompt calibration and reconstruction of the detector, which for the first time let us do physics without having to go through an expensive end-of-the-year reco, which saves us resources and time. So you can see here on the plot on the left that our out-of-the-box jet resolution matches in the various areas of 2023, for instance, the green ones, which are those that we obtained from 2018 data after the legacy reconstruction, so the RICO that we're trying to avoid. So out of the box, we got the same data quality that we used to have in 2018 after this post-processing. In the middle, you see the stability of one of the most complex algorithms that we perform, which is an artificial intelligence-based stagger to isolate B-jets that represent the jets as a point cloud and tries to understand if the jet is a B or not. The fact that this algorithm is stable across time is certainly not trivial. And on the plot on the right, you see the plot of the invariant mass distribution of Z dielectrons on the latest data, which remarkably matches in resolution the same distribution for run 2, despite the fact that the detector is aging and is collecting radiation. With this data, we already produced several results at past conferences. For ICHEP, we have 3 new results. We have our 2 first Higgs inclusive and differential cross-section measurements, both in X2 gamma gamma and X2 ZZ final state. And also, we studied the cross-section of WZ production at 13.7 TeV, at 13.6 TeV, that confirms the expected trend of the cross-section with the energy. Since the first year of the LHC, the challenge for us has been to cope with the intensity increase of the LHC without losing sensitivity. Our goal was to retain sensitivity to high-rate processes, particularly the low PT physics, without compromising the high PT part of the program. And we did this deploying 2 solutions. In 2011, we introduced data scouting as a way to work around the trigger constraints. So rather than storing the entire event, which is about a megabyte of data, we decided for the events that we cannot afford to keep, to store the form moment of the particle reconstructed at DHLT, which is about 10 kilobytes. And it's enough of information to do physics with it. In 2012, of the last year of round 1, we also deployed what we call the parking stream. So what we did is that to go around the limitations that we have downstream in terms of availability of computing resources, we just took as many data as we could. Those that we couldn't digest immediately, we put them on tape. And then during the shutdown, when resources became available because we were not taking data, we went back to those data and we reconstructed them. In run 3, we're pushing these 2 paradigms to an extreme. So scouting now processes takes 1 event out of 5 that enter the HLT. So, and at the same time, we promoted a parking program to a default. We don't wait the last year of the run to do it. We do it constantly. So this is going to be a big benefit for our core physics program, but it's also a way for CMS to develop strongly in areas that go beyond our core program, like investigating areas in flavor that normally we could not access. Data scouting was initially introduced for light resonance searches, the DiJet in red and the Daimyon in green in run 2. But today, it's a generalized paradigm. In the scouting stream, now we have all the kind of objects, photon, electron, taus. We can do any kind of physics with it. Because of the improvement in the HLT calibration that I discussed before, these objects online effectively have the same goodness, the same quality as the corresponding objects offline. So the view of the event that you have the HLT is not even degraded in resolution. It is as good as. So we are really capable of doing offline-like analysis in an online way. And also, we can push this to a very extreme of reconstructing complicated objects. Like you can see, this is basically a Z distribution in the decay of 2 hadronic taus that you get out of the box with this data. We expect this to basically give us an extra handle in the region between 1 and 100 GeV, which is the one which is challenging for the trigger. We're also rethinking the parking. So the way it works is that normally, so there are 2 ingredients in the parking in run 3. One is a set of loose triggers that would just take more data. And the other one is a set of triggers that we switch on when the luminosity profile of the LHC goes down. So normally you would see the luminosity going down that way, that way. Instead, now we switch on a set of looser and looser triggers that keep the rate high and give us access to an 80% pure sample of BB bar that, for instance, we can use it operating CMS as if it was a flavor experiment. So we extended also the menu of triggers, including, for instance, a loose BB bar plus stav trigger that is important to increase the acceptance of Higgs and double Higgs analysis. This is the example here. And also, we have a dedicated inclusive and exclusive vector boson fusion trigger, which let us collect a dedicated sample of vector boson collisions, so yet again exploring the LHC as a collider of other kinds of particles. First results from parking, already in Morion we showed this one, which is a search for new resonances decays to multi-jets displaced. So this analysis uses a third of the corresponding analysis run 2, but it improves its results by an order of magnitude thanks to a better trigger. And on the right, you have an analysis that 2 years ago, 3 years ago, was impossible to conceive in CMS, which is it's a search for D0 meson that goes to mu-mu. These muons are super soft. This is not the physics that CMS was meant to be doing. We can do this physics because of this parking data. Also, we've been very strong adopters of AI solutions, mainly to improve our traditional tasks like BJet tagging. Across the years, we went from a rule-based algorithm to deep neural networks to the recent graph nets and particle transformers. And we gained a factor 60 rejections of light jets while rejecting sequarks, which are more challenging to reject, by a factor 10 better than what we used to do. And also, now this very same paradigm, some of the same kind of networks are also used to trigger, to tag other kinds of jets, like boosted Higgs, boosted vector bosons, and boosted stops. But we're also using AI out of the box. For instance, this is something we call FlashSim, which is a super fast simulation of the detector that let us go from the generator level straight to the reconstruction level, skipping the heavy computing steps in the middle. But we do so not at the level of the particles in the events, but at the level of, we represent the event as the 100-ish quantities, the high-level quantities, functions of the full moment of the particles that typically we use to do data analysis. And we do this at generator level, and we use a normalizing flow to morph this 100-dimensional distribution into the corresponding RICO1. This way, we not only have good accuracy in the single quantity, but also in modeling the correlations between them. And also we have a good resolution. And now we are using the same paradigm in also to correct our Monte Carlo simulation whenever we have control sample. This is an example of a similar technique applied to do data to Monte Carlo to data and not Monte Carlo to Monte Carlo. And also we're using this technique to learn how to look for new physics in a new way. This is the example of a trigger implemented on a hardware trigger. So this is the footprint of the algorithm on our FPGA that let us select events that otherwise we would have lost. And these events, this is an example here, are unique events that are triggered based on the fact that they don't look normal. And you will hear more about that during Jennifer's talk. So this is just the beginning for us of an AI-centric evolution of CMS towards luminosity. At this conference, we have 37 new results. I'm not going to go through all of them. You have all the list here. I'm just going to highlight a few of them because there are a few aspects that I want to highlight. Number one is that, as Monica showed before for Atlas, we are increasingly probing lower and lower probability processes. We span 14 orders of magnitude in processes going from QCD processes to the multi-bosons. And we also have a program to measure the fundamental parameters of the standard model with several techniques which are different and redundant, and this let us gain in precision. We released the most, one of the most accurate determination of the sum square theta weak quantity using forward-backward symmetry in dilepton events. We passed the corresponding precision by lab, and also we managed somehow to release the tension in these measurements. We are doing precision physics with the Higgs boson, looking into differential distribution where new physics could pop up while being overwhelmed in inclusive measurements. So we combine several channels to gain precision. We interpret that in EFT, And so we can put lower bounds on energy as a function of different operators for different choices of decouplings. We have an extended search program. I'm not going to go through that. You have 3 review papers where you can find everything we are doing on dark sector, heavy neutral particle, and displays. We just want to highlight on the fact that all these searches are exploiting a huge amount of new signatures using AI, using a clever way to look at our detector. One highlight for this conference is the first statistical combination of our SUSY search program into an interpretation of the phenomenological MSSM. So this is giving us the big picture of what we've been doing with SUSY in the last 10 years. And what you see is that, so these plots show the survival probability of a given model to our analysis. And what you see is that we are challenging enormously all the models that have color particles below the TeV threshold. While for the light electroweak, there is still room, and this is where searches are concentrating now. This is another search that people have been asked us to deliver. So here it is. It's a search for a resonance that goes to Z that we're constructing for leptons. This is basically like the Higgs search in 4 leptons. We use the invariant mass of the 4 leptons and the matrix element of the 4 lepton decay to disentangle the signal in the background. So the reason why this was interesting, because people at some point started to claim in literature that there was an excess in Atlas data at 650. We don't see it. Also, we have an excess here, but this excess is not there in Atlas, so there is really nothing particularly concerning here. As a flavor experiment, we delivered the first study of a full hadronic charm decay. Again, D0 to K short is not something CMS is meant to see, but we can do it thanks to parking, because we can select BP bar events looking at one of the B, and then we have an unbiased sample on the other hand where we can look for this kind of stuff. And also we have the first CP violation, the evidence for CP violation in the BS sector, in the BS bar mixing in GeoSci-Fi, despite the fact that CMS doesn't have a particle identification. Basically, using AI, we managed to compensate that, deploying up to today the best B-flavor Jeff Tagger at Hadron Colliders. We also do a different kind of flavor, looking at TOP. For us, TOP is a laboratory which is very clean that we can use in order to probe flavor. This is an example where we look into lepton flavor violation in TOP decays. We don't see it, so we put bound in the 2 semi-leptonic top to U and top to C decays. But here, this is also very interesting. Because of this laboratory that we have, we can isolate hadronic W to quark decays that normally we cannot trigger on. And there, using an exclusive semi-leptonic C tagger, we can isolate the W to CQ and measure this ratio of branching fractions, improving it over the lab combination of the 4 labs experiments by a factor 2. And this actually can be interpreted with previous hour measurements that we did, that is a test of the unitarity of the CKM metrics. This very same top laboratory, we're using it to probe quantum mechanics, quantum entanglement at a high energy that was never done before. We have 2 searches. One is exploiting dilepton events at the threshold in a time-like dominated region. And the other one is looking at single lepton into the space-like dominated region, which is at the high mass. Both analyses establish entanglement at the level which is compatible with the standard model, and you'll hear more about this on Wednesday. Last 2 things. CMS as a photon collider experiment. We have an extended program in order to do this kind of physics, which is obtain combining different techniques. At very low energy, we take heavy ion collisions, ultra-peripheral, where the 2 ions see each other and exchange photons. At high energy, we have the corresponding process. This was the heavy ion. At the high energy, we have the corresponding process where we tag these protons, which are deflected, using Raman pods, which are collected far away from CMS. But now we have a new techniques that looks into the region in the middle, simply biasing with cuts the data sets towards collecting diphoton events. This is basically done asking for a low number of tracks coming from the primary vertex. And this, of course, requires very careful study and data-driven correction in order to get there. We obtained this way the first observation of tau-tau production, photo production, and with that we extract the most precise determination of G-2 of the tau. And the last topic is our heavy ion program. We have been fully engaged into study identity QCD. We have challenged our detector to do so with events which have high occupancy, large rate, and really challenge our system to the maximum. And a lot of the things that we learned have been then used as an experience to improve our capability with the PP run. So at this conference, we have two new results that look into the interaction between core group plasma and the outgoing jets that are emerging from the collision. In one case, we look at the imprint of the QGP on the jet, looking at energy-energy correlation function. In the other case, we take gamma plus jets events with the idea that the photon would escape without interacting with the medium, what the jet will do, and this introduces the correlation of the axes inside the jets that are measured in different ways. So with respect to the photon, you start to see that there is an effect. Both measurements challenge our current understanding of the QGP description, and so this is going to be the basis for improvement. So in conclusion, CMS is producing cutting-edge results on all fronts of collider physics, on the Higgs electroweak QCD, the flavor, top and light jets, heavy ions, and also an extensive search program. We're pushing our detectors beyond its capabilities. We are rethinking the way we operate it in order to maximize the physics reach, and we are endorsing AI-based algorithms to do things faster, easier, and better. The collaboration is fully engaged to this ambitious program, and we are delivering high-quality physics results while contributing to reshape the future of collider physics. And also, with a major upgrade ahead, we will expect that we're even getting better and better with time. Thanks.
Maurizio, thank you very much for a very comprehensive overview of CMS results. So now we have time for questions. It's very difficult to see from the stage here, so please stand up if you have any question here.
Thank you. How certain are you that there are not more Higgs-like Higgses, say in the several hundred GeV, 500 or a little above maybe? What searches have you done about that?
We're not certain of anything.
Pardon?
We're not certain of anything. We're certain of the fact that we didn't see them yet. We're actively searching for them. Basically, every single Higgs search is repeated higher masses. So far, we didn't see anything, but it doesn't mean maybe just the couplings are smaller. And so this is certainly a program that we will keep doing with more and more data. And also, when you start to go higher and higher in masses, you have new final states that open up, like the TT bar, that normally you would not look for under 25 GeV particle going to TT bar, but a large mass it can. And there are also these additional channels that we're probing. People are actively looking at that in run 2 data, in the run 3 data. And so this is certainly part of our mission, and we keep updating these results, and we're probing smaller and smaller and smaller couplings as a function of the masses. Then maybe something at some point will pop up.
Okay, thank you. There is one question over there.
Hi. On page 21, you are presenting the SUSE results of the combination of those, and you are talking about a combined survival probability.
Yes.
Now, I'm not sure what this means, but I guess the only one that is really meaningful is 0, and all the others are not meaningful.
It depends, no? So if you have a statistically meaningful population of SUSE models based on what you know from direct bounds, there you're measuring the impact on this population of the direct searches. So you see that the direct searches just dump down. So this distribution was flat in generation. So everything that predicts, so you are scanning this parameter, the stop mass. So there is a lot of models here that you test, and all these most of these models just drop down. And this is telling you that basically we're pushing to high confidence all the colorful particle above the TV scale.
Well, we don't have a measure on the parameter space, and as I said, the only number, and I agree with you, that makes sense here is 0. There you can say we exclude
I
it,
disagree on that, because the spirit is different. I'm not telling you that there is no stop. We didn't exclude the stop below 1 TV. I'm telling you what our search program is probing. And this is only part of the analysis list. We have way more than that. It doesn't mean that, okay, let's go home and burn all our books in supersymmetry. It just says that our searches are extremely sensitive to colorful particles below 1 TV. So unless your model falls into some very specific tricky places, most likely it's excluded. And then, of course, with this statistical analysis, you give us a spectrum, we can tell you if it's excluded or not.
Okay, there was one question over there.
Yeah, hi. Hi. At the bottom of page 20.
20. Yes.
What do you mean by disappearing jets?
So the disappearing jets, in models of, in dark sector models, so you are saying there is a gauge sector which is sequestered away from our gauge sector, and there could be some portals. These portals could be some particle of the standard model, or even some kind of Z prime, or whatever. In this scenario, there are two different signatures that you expect: the disappearing and the emerging jets. The case of the disappearing jets is a jet in which particles so you start showering particles in the standard model that eventually, through the portal, drops into this hidden sector, and then the outcome of that becomes invisible to you. So in the middle of your detector, your particle disappears. Like you have a track that in the middle of the tracker, you don't see it anymore. It went through the portal into particles that are invisible in your detector, and then it becomes invisible. The other way around, you produce particles in the dark sector, and in the dark shower, these particles, through the portal, come back to produce particles back into the standard model. And so in the middle of your detector, suddenly, particles appear. So effectively, you have a jet of particles, the same way we have it in QCD, except that or you have displaced particles, or you have tracks kinks that stop in the middle of your detector. So it's a different kind of jet that, again, our AI tagger, the same one that we use for bees, opportunely retrained with an extended representation of the particles in the input data set can handle. And this is what we're looking for.
Okay, thank you. We have one more question.
I'm here. My question is maybe a little bit difficult. I want that you mention one highlight of CMS. I am not sure you are prepared for such stupid question, but just give one highlight of CMS collaboration. What you would select?
But I would not select necessarily.
You have to select. This is my question.
Yes, I would not. I was saying, I would not select a physics result specifically. What I would select is this. So we are rethinking the way we run this instrument. And this is opening up opportunities. And we are not then yet done exploiting these opportunities. And so we just started scratching the surface of what this instrument can do. And we have a factor 10 data coming. We didn't even analyze this data in all these aspects. There's a huge amount of work to do. And so, as Monica was saying, the present is bright, the future is brighter, and we just have to go there and exploit this data. So that's my highlight.
Thank you. It was your choice.
Yeah, thanks, Maurizio. I'm happy that you brought up this slide. I had actually a question on this scouting. How far more you can go with that? Now you have 20, a lot? Yeah, okay.
A lot. I think that we basically, so far, we've been playing with it. We've been doing the obvious. We've been in what it is. Now we are saying, okay, this is really a game changer. And this is starting. It's getting attention of people within CMS that was not even paying attention to that. Scouting in the mind of everyone was a tool for exotic searches. And now there are people, they're doing standard model precision physics that say, oh, I could actually use it to do precision physics. And now, I honestly don't know anymore where the line of what CMS cannot do is.
Okay.
So we are basically trying to probe that now.
Thank you. So I think all of us look forward to this. Yeah, thank you very much. So are there any more questions? I don't see anybody, so let's thank all the speakers.